So after last week's lab, a lot of you discovered that that you might have forgotten or never learned vector geometry. This was my mistake. I just had assumed that you'd know about it, but now thinking back, I don't think I learned about it in the HSE either. So you may not have done it before. So I thought today we'd spend some time looking at it in more detail because it's a rather important part of what we're going to be doing in Unity. So some of what we're talking today is going to be computer programming. Some of it's just going to be a bit of math that is useful in thinking about 3D. And I hope I can demonstrate some of it in ways that make sense to you. Said previously, Unity, obviously we're dealing with 3D scenes, and so we're moving things around in three-dimensional space. So the important things we need to know about are vectors and quaternions. And the most important one here is vectors. We'll be spending a lot of time talking about vectors and a little bit of time talking about quaternions. Quaternions are a bit hard to understand, but vectors represent positions in the world and movement in the world, and quaternions represent rotations in the world. So if you're moving an object, you're going to be generally going to be using a vector of some sort. If you're rotating an object, you're going to be using a quaternion. Why they're called quaternions, I haven't a clue. So we talked previously about 2D geometry, where when you've got a big flat plane, you can number every point in the plane and according to its x and y position. And we said how you can extend that to 3D geometry by adding a third direction. So if that's x and that's y, then now that's z. And so every point can be its x, y, and its depths into the screen would be its z position. And obviously I can't put up a 3D slide, so that's what it looks like when I try to draw it on a 2D slide. And we just add another number, essentially, and we can add as many dimensions if we want, but going beyond 3 dimensions gets a bit weird. So we won't go anywhere beyond 3 dimensions. We'll be talking about 3 dimensions a lot. But in today's examples, because drawing 3 dimensions is hard, I'm going to stick to 2 dimensions. The ideas are really the same. It's just that you've got another option to go in depth as well as width and height. So, like I said, we can represent a point in the world, a position of something, by its x, y, and z coordinates. And so we can, if I want to talk about where we have an object. I brought an object with me. So here we are. We have a soccer ball. I can talk about where it is in the room by its x, y, and z position. So if I call that bottom corner of the room 0, 0, 0, then I might say, this is 2 meters x, 1 meter y, and 1 meter z away from that corner. And we can move it around the room, and every position in the room could have a different set of 3 numbers associated with it. But most of the time we don't want to think about these 3 numbers. We just want to think about the position as a point. It's there, or it's there, or it's there, and we want to talk about that point as a single thing. So the object-oriented abstraction allows us to just treat a point as an object and forget about what those components are. And so a lot of the time we won't worry about what x, y, and z are. We'll just say, here is a thing, it's at some point in the world. Here's another thing, it's at some other point in the world, and so forth. So now a vector is like an arrow pointing from one point to another. So if we back up a slide, if there's you and me in space, so I'm here down the front, and, well, actually we've got the room around the way, and you're up there somewhere, then the vector will be the arrow pointing from you to me, or the arrow pointing from me to you. Now, those are 2 different vectors. So the arrow pointing from me to you, we designate by the me minus you, right? So this is, we take me and we subtract you, and we get this arrow. Now why it's that way around, we don't really need to worry about, but if you go into working it out in terms of x, y, and z, you'll see that that kind of makes sense. If we want to talk about the arrow pointing in the other direction, that's you minus me. And so that's a different vector. That's a vector pointing the other way. So like I just said, if we have 2 points in the world, we can calculate the vector from one to the other by just subtracting take the destination and subtract the source. So it's 2 minus from. It's always 2 minus from to get the vector going from to. Okay. We can also add vectors to a point. So if we have a point, the source point is a point in our world, and we want to move that by the vector, then we can add that to the vector v to the source point and get the destination point. So the vector, if you can think of a vector as an arrow that has a certain direction associated with it and a certain distance associated with it. So if I show you, so if we have a point P there in our 2D plane, and we have a vector, the vector tells us what direction we're going to move in and how far we're going to move in that direction. And so if we add that vector to the point P, we get a point that's moved by that much. So we came from P and we added this vector, and so we ended up over here. So it really is just an idea of this is a movement in space or something like that, a direction and a distance. The direction, it doesn't matter where it's starting from. You can use the same direction and distance from any starting location. So if I have a different starting point Q, I add V, I end up at Q plus V, which is all the way up there. So the vector isn't fixed to any spot in space. We can apply it to any point in space and move as a movement to another point in space. So if I said in the real world, walk 1 kilometre northeast, then you could do that from any point in the world, and you'd end up in another point in the world which is 1 kilometre northeast of that. Now that'd be a rather long walk, and you probably have to go around things, but you get my meaning. So generally it's the description of a direction, northeast, and a distance, 1 kilometre. And you can apply that to any point in the world to get to another point in the world. So like I said, we can also add vectors together to make new vectors. So if I said walk 1 kilometre northeast and then 1 kilometre north, I could add those two together, and it would kind of be, well, if I said walk 1 kilometre east and then 1 kilometre north, that would be the same as walking about 1.4 kilometres northeast, right? I don't know if that makes sense, but we'll show you a worked example here. So if I told you to walk in this direction, however long V1 is, and then I told you to turn and walk in this direction, however long V2 is, then your final position would be the sum of those two vectors, which is this vector, which is the same as this vector, just saying walk that direction in whatever distance it is. Now, obviously the length the length of this vector is shorter than the sum of the lengths of these two vectors. So it's sort of like taking the short way rather than going all around the distance. So when you sum vectors, it's like the vector you result is taking a shortcut between the long convoluted route that you would take if you took every vector in turn. The same thing, and you'll see that if we did the vectors in the other direction, in the other order, if I told you to walk V2 first and then walk V1, you'd end up at the same spot. So in maths we say that it's commutative. No, it's something like that, commutative I think. Which basically means that if we add V1 to V2, it's the same as adding V2 to V1. We get the same result. So we don't need to worry about what order we add them in, which is a handy thing. So now the tricky thing is, when I talked about points and vectors as if they were two different things. But really a point is just a vector. A point is a vector from the origin. So if, like I said, if that point there, if that corner of the room is the origin, then rather than talk about this point, I can talk about the vector that comes from that origin to here. So if you started at the origin, how far would you have to walk and in what direction in order to get to wherever I am? So every point in the world can actually be described as a vector starting at the origin and moving to that point. So we don't treat points and vectors differently. Every point is actually represented by a vector. So in Unity code, the vector3 class, which represents a vector in 3D space, is the same class that we use when we're talking about a position as when we're talking about a velocity or a direction or anything like that. We just use this idea of a vector. Everything's a vector. So see what I mean. If we're talking about a point x, y in the world, we can also say that that's equivalent to the vector vxy, which starts at the origin and ends at that point. So every point in the world can be represented as a vector. Okay, so like I said, vectors have a distance and a direction. Now the distance of a vector is what we call its magnitude, or we might call its length. In Unity it's called the magnitude of the vector. And if we look at the vector, you look at the vector 3 class, every vector has a property attached to it, which is its magnitude. And that's the dot magnitude property. So if we want to know how long a vector is, we can just look at the magnitude property and it'll automatically tell us how long that vector is. So if we wanted, for example, to calculate the distance between 2 points, we'd find the vector from here to here by subtracting 2 minus from, and then we'd find the magnitude of that vector, and that would tell us how far you are away from me, or how far, whatever the distance is between our 2 points. So that's a frequently used property of the vector that we want to talk about. We'll say, okay, how far, for example, if we're making a game and we want to know how far the enemy is away from the player, we might want to be doing some tests that if the enemy is too close to the player, then something bad happens. And so we could say, okay, get the enemy's position, get the player's position, subtract them to get the vector between them, and then use the magnitude to calculate the distance. And then test that to see what we want to do with it. No, I won't go into that. There's also a property called square magnitude. It's actually faster to calculate the square magnitude than the magnitude, but most of the time, sometimes you just want the square magnitude, so it doesn't matter. But it doesn't really, you don't really care about that, so we'll move on. So hopefully you all remember Pythagoras' theorem from way back when, which says that if we have if we have this vector from the point 1, 2 to the point 5, 5, then the distance or the magnitude of that vector therefore is the difference in the x positions. We take the difference in the x, which is 4, the difference in the y, which is 3, and we use Pythagoras' theorem, which is that the length of the hypotenuse is equal to the sum of the square of the length of the hypotenuse is equal to the sum of the squares of the other sides. Good grief, it's been a long time since I said that. So in other words, this length is d squared is 3 squared plus 4 squared, which is 9 plus 16, which is 25, so d is 5. So so the length of that vector is 5. Now you don't need to care about that because if you provide those 2 points in the world, the magnitude gets calculated automatically. So the computer automatically does this computation for you under the hood. All you have to do is ask it what its magnitude is and it'll tell you. But this is another example of abstraction. This is the process, the calculation the computer's actually doing, but you don't have to care about that. All you have to say is, here's a point, tell me what the magnitude is of that vector. But it's worth knowing what it's doing if you have some idea. So once we've got a vector that has a certain distance attached to it, we might want to scale that vector, which means to either stretch it or shrink it by a certain amount. So we might want to maintain the distance, maintain the direction, but scale it. So I say, okay, so whereas before it's the distance from you to me, we've got a vector from you to me, from you to me, okay, a vector going that way. It has a certain length, but I'm interested in scaling that down to a short version of that vector. And so what I can do is I can either scale it down or scale it up. If I can multiply a vector by a number. If I multiply it by a number bigger than 1, then it's getting bigger. If I multiply it by a number less than 1, it's getting smaller. Or I can divide it by a number. So if I want to take a vector that's twice the length, I can multiply the vector by 2, and I automatically get a vector that's twice as long. If I want to have a vector that's half the length, then I can divide it by 2, and I get a vector that's half as long. Now these vectors, double and half, are still pointing in the same direction as the original vector. If I scale by a negative number, I get a vector pointing in the opposite direction. So if I multiply by negative 1, I get a vector of the same length, because I'm multiplying by 1, but negative, so it's pointing in the other direction. If I multiplied by -2, I'd get one that was twice as long and pointing in the opposite direction. So in a picture, if this is the blue one is our vector v in the starting case, v times 2 will be a vector pointing in the same direction but twice as long. V over 2 will be a vector half as long, and -v will be a vector pointing in the opposite direction. This is useful because sometimes we'll have a vector going one direction and we'll want to invert it to have a vector going the other direction, or we want to stretch it or shrink it, and so we can do this sort of scaling. Sometimes we want not to multiply the length of a vector, but to set it to a known size. So if I have a vector of length 4, I could scale it up to a vector of length 8 or down to a vector of length 2. But if I want to turn it into a vector that is exactly 1 unit long, then I have to divide it by 4. Now, if I have a vector of length 8 that I want to turn into a vector of length 1, then I have to divide it by 8, and so forth. So this is called. So the thing we can't do is directly set the magnitude. Magnitude is a read-only variable. If you look in the docs of vector 3 on the web, it'll tell you that magnitude is read-only, which means that you can't assign a value to it. So if I have a vector and I want to make it a certain length, I can't do this. I'm not allowed to say the magnitude is equal to 1. It just doesn't work that way. What I've got to do is doing what I call normalising it. Normalising a vector means taking a vector and turning it into a vector of length 1 in the same direction. Every vector in Unity has a normalised property to it. This is a copy of the vector which points in the same direction but has length 1. So if I want to normalise the vector, I can set it to its own normalised value. Note that it's an American spelling, it's spelled with a Z. Almost all programming languages use American spelling, unfortunately, which is really annoying, but you have to deal with that. So you have to learn how to spell colour without a U, and you have to learn how to spell normalised with a Z and things like that. It's creeping imperialism, if you ask me. So we can normalise the vector in order to make it of length 1. Now, like I said, the normalised vector has the same direction but a certain length. If you want to set it to a different length other than 1, we can normalise it first and then scale it. So if we normalise it to length 1 and then scale it by 4, we end up with a vector of length 4. If we normalise it and then scale it by half, then we end up with a vector of length half, and so forth. So, I thought I had a picture of that, but I don't have a picture of that. So normalising is a way to set the vector to a known length. Now, there's one thing you should be aware of here, which I didn't write down in the notes. So this is only for people who come to the lectures or watch the videos. There is the 0 vector, which is the vector that goes from here to here, right? That's the vector that represents no movement at all. Now that vector always has length 0, right? There is no way to, if you stretch it, it'll still be 0, because the movement from here to here, no matter how many times I move from here to here, I still end up here, right? So I can scale it as much as I want, and it's still 0. So it's like multiplying 0 by any number. You multiply 0 by 4, you get 0. Okay? So you can't normalise the 0 vector because you can't make a vector of length 1 that doesn't go anywhere. Every vector of length 1 goes somewhere. The 0 vector doesn't go anywhere. So if you normalise the 0 vector, you'll get back the 0 vector. It's the only vector that can't be normalised. Any other vector can be stretched or shrunk to make it of a known length. The 0 vector is always length 0, and no matter how much you stretch it, it'll still be length 0. So you can't normalise the 0 vector. Usually this doesn't affect your code too much, but sometimes you've got to think about what it means. If you're expecting your object to move every time you translate it by a certain vector, and if that vector 0, sometimes it won't move even though you expect it to. So you've got to, one of the key things in programming, which I tried to get you to think about in that first exercise with sorting the cards, is you've always got to think about those edge cases. What happens when, sure, I've got a general process that works when I have 5, 10, 15 cards, but what about when I have 0 cards? Or what about, 0 is always one of those tricky cases in programming, that sometimes a program which works for any number other than 0 doesn't quite work for 0. So you've got to, when writing your code, think about those edge cases. What happens when this value is 0? Does my code still work? Or will my code die because I'm giving it a value, I'm trying to divide by 0, and that would be really bad. Anyway, so, but normally any other vector, you can normalize to a certain length. Okay. So that's dealing with vectors. Then when you want to use them, usually we'll be using a vector for moving something around. And the way we move something around is look at its transform component. So if we've got an object, a game object in Unity, every object in the world has a transform attached to it. If you look, in fact, if we go change down, whoops, let's go down here. Like I said before, every object that we pick, we haven't got an object at the moment, let's make an object to create other. Let's create a sphere in the world. There's a sphere. We can see over here in the inspector that that sphere has a transform attached to it. And the transform has 3 parts: a position, a rotation, and a scale. At the moment, position and rotation are all zeros, and scales all ones. So it's sitting at the origin and has no. It isn't rotated and has no scale. No, it's normal scale. Let me go back to here. Play. So, like I said, the position is a vector. It's the vector from the origin to whatever point in the world we are. The rotation is a quaternion, and I'll get onto those in a little while. The scale is also a vector. Now that's kind of cheating because the scale isn't a direction, but because the scale is 3 numbers, how much you stretch the x, how much you stretch the y, and how much you stretch the z, they're using a vector as a convenient way of representing that. Now, in a sense, the idea of a vector doesn't really match to the idea of a scaling something. But it turns out that that in some ways it's useful to be able to treat scaling as also a vector. But I mean, from your point of view, scaling something just means you're stretching it in x, you're stretching it in y, you're stretching it in z. So that's 3 numbers which make up a vector, and we don't really need to worry about the geometric interpretation of that. To get at this transform in our code, we have a variable. In any script, there's a variable called transform, which accesses the transform component of the current object. So whatever object has the script attached to it, the transform variable will give you will give you access to that transform. So if I just want to move the object that the script is currently attached to, I can take the transform.position and I can add my vector to it. And here we're using that shorthand notation, which is you take the old value, you add v to it, and then you assign the new value to it. So we can move an object by taking by adding something to its transform.position. If we want to get at the transform of another object, then we need to get we need a reference to the object. So a game object is a way we refer to a different object in the world. And if we have a variable v, which is that game object, then every game object has a transform field on it as well, which tells us the transform of that game object. So if we have a game object in the variable g, we can look at the transform.position of that, and if we wanted to move that object, we can add a vector to that, or whatever we want to do. So we're going to do a worked example now, because that's all a bit abstruse. So let's go down to here. I'm going to see if I can make things a bit clearer. Let's add. So I've got that sphere in the world. Let's add a plane. There we go. That's nice. And let's take our sphere and move it up we move it up a little bit so it's sitting on the plane. I think it should be about, whoops, that's the plane. 0, not the plane. We want to move the sphere. So we'll move the plane, move the sphere up. There we go. So now we've got the sphere sitting on the plane. Oh, and that's visible on the screen. Not bad. Okay. In fact, what we'll do, just to show you something kind of interesting, I've come over here. This is CG Textures website, cgtextures.com. This is a free site for downloading a bunch of textures. Let's pick a texture. Pick a category. Any category? Anybody favouring any idea? What do you want? Food? Ground? Let's make it. Let's food. What have we got? Fruit. That looks good. Okay. There's textures for. Okay, so we want a texture that is the outside of a piece of fruit. So if we take, say, this one, or okay, that one. Wonder what that looks like. Okay, lovely. What is it? It's fruit 17. Okay, it's melon. Okay. So if we click on that one, should be able to. There we go. Download that. We'll save that onto the desktop. Where's my desktop? Desktop. There we go. Desktop. Save that thing. Okay, it's finished downloading. So now if we come down back to Unity, and again if I go Assets, Import New Asset, and pick that colour that I just imported, hopefully that will import. Dum-de-dum. Yes, there we go. Okay, so now if we take our sphere, okay, so this is tricky. To colour in an object, it needs to have a material attached to it. So if we look over here at the mesh renderer, the mesh renderer is the, let's zoom in on that. The mesh renderer is the component that decides how an object is displayed. Every mesh renderer has materials, a bunch of materials attached to it. Normally there's just one, and the default is this default diffuse material. That means that this object will get displayed looking like a grey blob, which is kind of boring. So what we're going to do is come down to our project. We're going to create, oops, this is hard to do with the zoom on. We're going to create a new material. We're going to call this skin. And go up here, we've got a new material, and we want the material to be, yep, that's all right. Okay, cool. So the diffuse, now we have an option here. One of the things in our material is a texture 2D, it's called here. So what we can do is come down to our fruit skin and drag it up to there and drop it in there. And hopefully now, okay, all right. So we've now got a material that sort of looks like a fruit skin material. Now what we've got to do is go back to our sphere, pick up our skin. Actually, I'm going to zoom this out because that's just getting confusing. Pick up our new skin material and replace the default diffuse thing with skin. And now there is our ball with a skin on it. So that's how you go about actually adding textures to your objects in the world. So if we look at that in the game view, now we haven't got any light in the scene, so it doesn't look like anything. So let's add a light. Game. Let's create other point light. Let's put the light up about there. Where's the camera? So a lot of you noticed when in last week's shoot we're getting a bit lost in the scene. Remember these especially, it's hard to work out in the 3D view whether or not that camera is actually pointing at that ball. Very handy to use these different views. You can see now that camera, yes, it's pointing in the x-axis. So from above, yes, it's pointing the right way. From the side, yes, it's pointing the right way. And so we know that it's actually pointing at the object. If we're just trying to position it in this view, it's very easy to get lost and not know where it's actually pointing. So I noticed a lot of people ended up putting models in the world that were an awful long way away from the camera and a lot smaller than they thought. And it's useful to zoom out, to go into the top-down view, zoom out until you can see both the object and the camera in your view, and then work out where they are and move them towards closer to one another. So now if we have a look at the game view, we have there a moodily lit sort of round lemony looking thing. A nice artistic. I might actually move the camera. Let's put the camera instead. Let's take the camera. Let's put the camera here. And let's rotate the camera so it's pointing down. So to point down, we rotate around this axis, right? That's the x-axis. So we should rotate 90 degrees around the x-axis. Now I'm not sure whether we're pointing up or down. Ah, we're pointing down. Good, okay. So now we can, oops, don't do that. Oops, oh, just undid what I just did. 90 degrees, I can grab that, move it up a bit, move it over there. Now if we look at the game view, nice top view of our moodily lit grapefruit, maybe? I don't know what it is, anyway. Okay, so that was just a bit of fiddling around. Let me just move that up a bit more. Lovely. So let's now make this thing move. So we have, let's take the move script that we had previously. And we can actually, we'll just add that move script for the moment onto our object. And now, so what we did previously, was we just took a direction, which was a vector, and we moved the object by that direction, and we scaled it by the amount of time that we had available. So, so what you see here is what I just described to you. We have a position which is the current point in the world. We have a direction which is a vector. So this is the position is a vector. We have a direction which is a vector. We have time which is a number. We multiply the vector by the number, the time, in order to because the vector is our velocity, so it tells us how far we move per second. We multiply it by the number of seconds that passed, and we get a scaled vector that should be how much we move in that much time, and then we add that to our position to get our new position and go around. Now it was fine when we had a particular direction vector that we wanted to do, but now let's go through what we were going to do in the tute. If we have a target object, so I'm going to say we have here another field which is going to, I'm not going to call it G because that's a stupid name. I'm going to call it target because that's a much more meaningful name. So we have a field on our object which is that we're moving towards a target. So we're going to say move the object, whoops, not that, don't ignore that, stupid keys. Move the object towards a target. So there's our target. We also have a fixed speed at which we move. So we'll have speed, which is a float, and let's put a comment here, in units per second, whatever distance units we have. Okay. So now if we want to move, so first of all we need to calculate the direction that we're going to move. So the direction that we're going to move is direction equals, now like I said before, it's a vector from me to you, is we subtract your position, we take your position and subtract my position. So we take the target, we access its transform, which is a field of that object. We then get the position field of that transform, and that's your position. Now, I hate it, keep confusing the keys on this keyboard. Okay, so that's your position. Target.position is my position, because transform.position is my position, because the transform variable always refers to the object that we've got. So that's the direction we want to move in. It's a vector from the current position towards the target. Now that vector is as long as the distance between me and you at the moment. And so if we moved by that much, we'd move instantly to your position, which is not what we want to do. We want to move by a known speed. So what we need to do is, in order to move by a fixed speed, is to take that direction vector and then scale it down to a fixed length that we know. So we take the direction vector, we now assign, we can take the normalized version, because we want to move by a known amount. So we're going to normalize it so it's length 1, and I got the spelling wrong, normalized with a Z. Excuse me. We multiply by the speed, which now scales it. So if we're if we're moving at 2 meters per second, we've now doubled the length of that vector. Now, if we're moving at 2 meters per second, we haven't doubled. We've taken we've turned it into a vector of length 1, and then we've doubled that to a vector of length 2. So we by normalising it, we get a vector of length 1. We double that to get a vector of length 2, which was how far we'd move in 1 second. But we don't know whether 1 second has passed. What we're going to measure is how much time has passed, and therefore how far we should go. So if 1 second has passed, we should move 2 meters. If half a second has passed, we should move 1 meter. If 5 seconds have passed, we should move 10 meters. So what we need to do is scale this vector again by the amount of time that's passed. So now we take the same vector and we multiply it by, and I said that time, if you remember from last week, time.delta time tells us how many seconds have passed since the last time we did this. Now that code hopefully should move us at a fixed speed towards the target. So now if we go back to our world, we've lost our, there we go, okay, we're still looking at this, so cool. That's good. Okay, let's take the top-down view so I can see what I'm looking at. There we are. Okay, we need to add a target now. So let's pick another object in the world. Let's just make it a cube. And let's take that cube. We've got the cube, we grab it and we drag it over here. And we'll put it over there. And we'll actually have to move it up a little bit because it's currently embedded in the plane. That should do. Let's see if that looks right. There's our cube. Cube doesn't have it. Well, you can't see the cube because it doesn't have a texture. Actually, let me change this light. I don't like this light. I'm going to take out the point light, so we can delete the point light, and I'm going to add a directional light instead. Directional light. Now, a directional light. If we go look at it from the side, a point light is like a single light bulb that shines out in every direction. A point light is like you had massive light all the way across and it just shines down. And so we can, at the moment it's pointing out to the right hand side of the screen, but we can rotate it around so that it's pointing down. So if we just rotate that, again, if we rotate that by 90 degrees there, that looks better. Now if we look, now we've lit up the entire table because that directional light is just light from the sky coming down rather than light from a point coming out. So the shadows look rather different. That cube looks wrong now, so I'm going to just add another. I'm going to actually just to show you how to do it, going to add another material. This case, I'm not going to add a texture. What I'm just going to do is grab this and make it red. Okay, I'm going to call that material red. No, I'm not going to do that. I'm going to call that material red. There we go. So all I did there was I didn't add a texture, but I changed the main color. And now that's something that has no sort of texture to it. It's just uniformly red. And so now if I drop that on the cube, hopefully, there we go. The cube is now red. Lovely. Now if we go back to our sphere, and this thing's reporting an error, so let me have a look what that is. Failed to load window, yeah, that's probably not important. Let's just ignore that for the time being. Okay, so we've got our sphere, we've got our move script. We're not specifying a direction this time. Instead, we're specifying a target. That target is the cube, so we drag the cube across and put that as our target. And our speed, we're going to make the speed 0.1, for example. I don't know exactly how fast that is, but we'll see. And now if we play, hopefully I did something wrong. Okay, yay! Now I get to show you how to debug because my sphere's not moving. What did I do wrong? This is a good question. Let me have a look at that script again. What have I done wrong? Anyone spot the mistake? I love it when examples don't work in the middle of class. Okay, 1.0. Just make sure I've saved that. Sometimes you forget to save the script and it doesn't. Decimal point where? Oh no, the speed, because the speed is a. Oh, that's all right. No, it should be fine. Okay, why is it not moving? This is very slowly. Oh, it is moving just very slowly. Okay, so I thought I got the scale of things wrong. Okay, so that's just because I got this. Okay, that's cool. Oh, do I? Ah, thank you very much. Somebody on the ball. I multiplied it by, I scaled it down twice, so I was moving very slowly. Thank you, whoever that was. Well spotted. So now if I do that, That's much more reasonable speed for it to be moving. It's looking a bit jaggy, I don't know why that is. And it stops when it gets there because the direction vector becomes 0, and so it doesn't have anything to move anymore. In fact, if we scale down the cube a little bit, it might be interesting to see, we make that 0.1, 0.1, 0.1. So it's a little cube. There it is. You might see an effect happening here. Yeah, I don't know if you can see that, but it's actually vibrating. It's not sitting perfectly still there. It's actually going. What's happening is that it says, okay, I've got to move. So it's just saying, there's my target. Well, not all the way over there. You probably can't see that anyway. But I've got to move there. So the direction is that much. My speed is 1 meter per second. So in 1 second, I move to here, and now I turn around, and then now I go, what do I do now? Oh, the object's over there, so my direction is that way. I move 1 feet a second, and I end up here. And so what it's actually doing is every frame it's overshooting the object. So that's a bit of a problem. And so it's sitting there going past it and back again and past it and back again. That's annoying, but that's the way it goes. We can fix that later. All right, so that's the basic idea of how to move towards something. And I've got the feeling that, oh, okay, we've got a bit more time. Okay, so there's the code for doing that, and I've commented it there. This is showing you sort of what's happening when you execute it. So there's an object. So this is the object which we've got the script on. We take transform.position, which is this point here, and we assign it to from. We take the transform.position of the target, and we call that to. We take the vector v, which is the direction from to to. I don't know why I named them those things, from there to there. Okay. We then normalize that to reduce it to length 1, so that its magnitude is now 1. We then multiplied it by the speed, and so if the speed was 2, we would now have length 2. We then scaled it down by how much time passed. So if the time was only half a second, then we should only move 0.2 meters. If we were moving at 2 meters per second, then in 1/10 of a second we should move 2/10 of a meter. Right? And then we added that to the previous position, and we got a new position, and we assigned that position back into the object. And by assigning it onto the object, we move the object. And so that's essentially how that works. Now, since translating is a very common thing to do, there's also a shorthand for that plus. So where we had up here, transform. Okay, so here I've written a shorter version of it. Transform plus equals v. So before I had transform equals transform plus v. So this is a shorter version by saying plus equals. An even shorter version, which saves you slightly more characters if you really want to be concise, is translate v. This is probably the best way of writing it because it makes it clear what you're doing. It's actually translating, it's taking an object and just translating it by a certain distance. So you don't need to even worry. Now we've abstracted away all the vector math in that particular instance and just said translate by this vector. Okay, so I'm going to do a very quick version of rotation. Rotation is a bit confusing, so if you don't follow this, that's all right. We'll try to. I might cover a bit more of it in next lecture, or I might say we don't need to worry about it. So rotations are represented by quaternions. So when you're in 2D space, the rotation is easy because there's only one way to rotate things. You start pointing that way, and you rotate either clockwise or anti-clockwise around that way. Okay. So all rotations are in this plane. The problem is in 3D, there are lots of ways of rotating something. So if I had a ball like that, I could rotate it that way, or I could rotate it that way, or I could, oh, I've done that one. Which other one? Oh, I could rotate it this way, or I could really rotate it about any combination of axes that I want, right? So, so rather than, there's a whole bunch of matrix math that you don't want to know about underlying quaternions. What you want to think about is every rotation, we pick an axis. So that's the axis. It's a vector pointing out that way, and we pick an angle that we're going to rotate it, say 180 degrees, and that's a quaternion. There's a different quaternion for that axis and a different angle. So every axis that we pick and every angle that we rotate gives us a different quaternion. So a quaternion is a way to represent, just like a vector is a way to represent a movement, a quaternion is a way to represent a rotation. And then we can apply that rotation to different things. So if we have a rotation that is spin 90 degrees along the y-axis, like that, then we can apply that rotation to any number of objects in the room. I can tell you to spin 90 degrees, and then you to spin 90 degrees, and so forth around the room. You can have a look at the docs. We won't go there. So an illustration of that, if we think of a vector in the zx plane, so I'm trying to indicate that we've got the floor of the world in a sense. And we've got some vector which is just a movement along that floor. It has no y component. It doesn't go up or down. So then the quaternion, to construct a quaternion, the code is a little bit ugly, but we say quaternion dot angle axis. And this is the axis, which in this case is the up vector. So there's a name for the up vector, so that we can always use the name vector3.up. This is the angle that we want to move, and so here we have the vector. Here we have the up. The axis is the up vector, which is the same as the y vector over there, and this is the angle that we're moving. And so we rotate in the plane from there to there. Now, if we wanted to rotate something about the x-axis, then we'd be rotating in this y-z plane, and the x-axis would stay the same. So the axis is the direction that stays pointing in the same way. So if I tell you to turn according to your y-axis, which is up, then your head, which is the top of your body, still points in the same direction. The rest of your body turns around. If I tell you to do it in the x-axis, then my arm would stay pointing in the same direction, and the rest of my body would rotate around it. So every rotation has an axis that stays the same and a rotation that turns around, that spins around that axis. So then if you want to, say we want to make that ball that we had in the thing rotate, spin as it moves along the ground. So at the moment what we've got is a ball going, just hovering like that, which isn't very interesting. What we want to see is it actually roll along the ground. This is a kind of tricky example, but hopefully you get the idea. The axis of the rotation, so if I'm going from here to there, the axis of the rotation is that way, right? The axis is, where's my pen? I've dropped it there. So the axis of the rotation is actually that way, because that's the point on the ball that isn't moving, that isn't rotating. The angle is then proportional to the distance travelled. So the further I move, the more it rotates. So if we have a rolling ball in 3D space, and this is the vector, and we assume this vector is parallel to x and z, so it isn't going up or down, it's just moving along the ground, then working out the axis is a little bit tricky, because the axis depends on which direction you're going. If the ball's moving that way, then the axis of rotation is that way, and it's always at 90 degrees, right? And if I'm moving that way, then the axis that I'm rolling is that way. So what I need to do is say, that's my direction of movement, that's up. So now if I rotate by up by 90 degrees, I end up pointing along the axis. Now, is that clear? Right. So if the ball is moving along the ground, it's moving in that direction. If I rotate, I'm about to, stupid, I always plug play, then, so there we say, okay, the axis is then by the rotate around the y-axis. The distance that we roll, the angle that we roll is well, because it's a circle, the amount,